paying attention.
Okay,
Right.
we've had this blue one. We're going to go over that in just a little bit, okay? With the free body diagrams. We've turned in vectors of doom.
Oh man, this meeting.
But before we do our free body diagrams, we need to talk a little bit about forces in general, okay? Yes, and I gave you the pink packet of what you absolutely have to know about forces to pass the AP Physics B exam. That's your reference, okay? We won't go over that specifically, but that's just to kind of help you through forces. It's got about 10 pages. You can, it's your review for forces, essentially. All right?
So we won't do this with you?
What's that?
We won't do it with you?
I'm not going to go over this one with you. Not like the one we did with thermo, where we pretty much just followed that. This one's more for you. It's kind of just a review of forces to help you review for the exam, all right? Kind of the different steps you use to solve force problems, all right? And most of the types of force problems that you'll run across, okay? All right, impulse. What's impulse?
Change of
Some of the
That's
forces
true, but what is this?
Some of the forces delta T.
F
Oh,
delta T, right?
Yes.
And this can be written change in MV, right?
Yes.
which
All right.
is just basically most of the time interchangeable.
Most of the time, M is constant. If mass equals a constant, then it becomes F delta T equals M delta V. If we divide both sides by delta T, mathematically that's correct. And we get the sum of the forces equals M delta V over delta T, which takes us back to F equals MA. All right, we've already done this in the other order. We're just taking us back from what we already learned. Momentum is impulse equals change of momentum. That's another way of stating, another way of writing, essentially, force equals mass times acceleration, or the sum of the forces. If there's a net force, okay, if these forces don't all cancel, then there will be an acceleration. And the thing is that this force and this acceleration are in the same direction, okay? They have to be. Now, let's get something clear right away. Okay, I keep saying sum of the forces, that's S, U, M, not, yeah, oops, I almost wrote on, not S-O-M-E. Okay, I just want to make this clear, everybody. It's S-U-M, not S-O-M-E. Hey, that seems kind of silly, but one year I kept saying the sum of the forces. You're supposed to say the sum of the forces equals mass times acceleration. And I would just say sum of the forces equals MA. And I had this poor student raise their hand and they said, "Hey, Mr. Bruin, I'm totally confused. Which ones?" I'm like, "What do you mean, which ones? You keep saying some of the forces. Which ones are you picking?" And I'm like, no. All of them. Every time. All right? Let's clear that up. And it totally made their day.
Aww, you made someone's day.
That's right. Okay, everybody? So we're talking about these forces. All of the forces interacting with an object. All right, F equals MA. The deal is that whatever the object is, whatever the number of forces are on the object, okay, when you sum them all up, if the net force is some value, okay, if it's not equal to 0, then you're going to have an acceleration, okay? And the acceleration and the force will be in the same direction. Okay, they have to be. That does not necessarily have to be the direction that the object is going. Did you catch that?
Yeah.
Acceleration is not necessarily in the direction the object is going. All right? Common example is throwing something into the air. The acceleration is down, but it could be moving up, right? In fact, remember trajectory motion, you throw something across the room, the acceleration is down even though the object's going at some angle, right? Okay. So acceleration is not the same as velocity, right? It's just the direction and amount to which the velocity will be changing toward. Okay, that's what acceleration means. All right, now this acceleration could be two types of acceleration. Remember, we got two types. We got a change in speed type of acceleration, and we have a change in direction. Okay, so we can have either one. We're going to talk mostly about this one at first. We'll talk about the change in direction one a little later. Okay? Because that one is a little unique. But we can have either kind. So any object that is changing speed or changing direction has an acceleration, therefore it has to have some sort of net force on it. Okay? Okay, let's start running down our laundry list of forces. Because we've got lots and lots and lots of them. Okay, so let's start our list over here. Start giving me a list of forces. What do we got for forces? Gravity, spring,
Tension.
tension, normal, friction, electromagnetic. We'll go electric, and we'll go magnetic. Any others? Ooh, we have strong force and weak force. Any others? How about weight? Weight is really gravity, right?
Yeah.
Okay. Any others you can think of? Let me see. Weight, gravity, normal, friction, tension, spring.
Drag is just another form of friction. So.
You could have drag. Little creature. All right, is that about it? Yeah, that's about all I can think of off the top of my head. All right, so let's start going down the list of these and deciding how these all work. Okay, let's start with the easiest one. Weight. Weight equals mg. Now this is really gravity. Okay, gravity is your weight. You have weight because of gravity, right? And this one is always down. All right, and this one is, if you're on the Earth's surface, you can use this. If you're on a mountaintop, if you're an astronaut, can you use this?
No.
Well, if you're in space.
It's gonna be.
Good point. Very nice. It depends if you're in space. Let's say you're in space and you're an astronaut.
It depends also how far apart you are, but it's gonna be less.
Okay, so the deal is this is assuming, weight assumes that you're on the Earth's surface or very near the Earth's surface, right?
Yeah.
Okay, because we assume that g equals 9.8 meters per second squared, or meters per second, thank you. This is, we're assuming this to be constant. In reality, it's not really a constant. It's the average across the Earth's surface, okay? People on the equator actually have, in general, a smaller value. And the reason why is because they're on the equator where the Earth is spinning and the Earth is trying to spin them off. Okay?
So they can have more mass, but they can weigh less than us.
Correct. If you live up on top of Mount Everest, that will not be 9.8. It'll be 9.7. It'll be slightly less. I don't remember what it is exactly. Depending on where you live on the Earth, depending on what's underneath you, the Earth is not uniform. And so if you live above rock formations that are more dense, like if you live above a lead mine or a uranium mine, you might weigh a little bit more. Okay? All right, so it varies across the Earth. Actually, if you're on the North or South Pole, in general, your acceleration due to gravity is greater than if you're on the equator. Because at the equator, the Earth's trying to fling you off, but gravity's too great. So it's a little bit less than that. Okay?
So about how much would the constant be, the gravitational constant be along the equator?
You know what? I don't remember. I have to look it up. It's not a huge amount of difference. It's not enough for you to notice. It's enough to measure, but not enough to notice. I mean, it's going to be 9.7 something, right? So it's not a huge difference. A few percent, and that's it. All right? Now, so we're assuming this only near the Earth's surface, but there's also gravity in general, and that is, do you remember that one? We generally use F sub big G for that one. Sometimes for this you'll use F sub small g. Force of gravity near the Earth's surface, force of gravity in general. Y'all remember what that one is?
Big universal
There's a big G,
M1, M2.
M1, M2 over R squared. And there's a negative sign. And the reason why there's a negative sign is because it works like this. Here's the sun. Wow, that's a crazy one there.
Why would the sun be wearing shades?
So bright. Because it's bright.
It's cool.
That's right. Okay, and say here's you. Okay, the sun's gravity on you works like so. The radius from the Earth out to you is this way. Radius is always positive, right? There's no such thing as a negative radius. So radius is 0 or positive. So that goes out that direction. But which way does the sun pull on you? Towards. So it's negative compared to the radius. That's what that means. So the force of gravity is in the opposite direction of the radius. Okay? That's why we have the negative. In most cases, students will neglect the negative and just put absolute value signs around there and just decide which way gravity force is. Okay? That's fine. That's what I do most of the time. Just find the magnitude and then decide the direction. Okay? Now, M1, M2. So this would be M of the sun, M of YOU. All right? That's the radius in between. And then you have big G. Big G is 6.67 e to the negative 11 Newton meter squared per kilogram squared. That's on your constant sheet. Get out your constant sheet and make sure you can find it. Because I have that one memorized because I've used it many, many years, but you probably don't. And that's okay. Just look it up. Some of you have it memorized. It's like Avogadro's number. You know what? Sometimes I remember it, sometimes I don't, because I don't use it very often. All right, it's right. There it is. It's on the right-hand side, in the top right corner. Now, do they have a different set of units?
Meters cubed.
Meters cubed. What, kilogram?
No,
Per kilogram.
Oh, per kilogram second.
Squared.
Okay, let's see if our units are the same. All right. Okay, we've got a Newton meter squared per kilogram squared. All right, what's a Newton? Okay, a Newton is, go back here. Here's where we get Newtons. And this is a kilogram, and that's a meter per second squared, right? So a Newton is a kilogram meter per second squared, because that's a mass and acceleration, right?
Yeah.
So if we plug that in there, we get a kilogram meter per second squared times meter squared over kilogram squared, and we end up with that, right?
Wait, but the kilograms.
That one cancels that,
Okay. Alright, there you go.
and then you get a second squared in the denominator and meters cubed, right? So it's the same thing. They just got rid of the Newton and turned it into basic units, okay? There you go. All right, now an interesting thing occurs. If you realize that you have gravity Oh, by the way, what if you have more than one object? Say like the Earth is out here, okay? And I want to find the force of gravity on you.
Net force?
Yeah, you got to solve this one time, right here. You got to solve it another time for the force of gravity on you from the Earth. And then you have to add those two up to find the net force, okay? All right. That, by the way, is how they found, which planet? Was it Neptune? Or Uranus? I think it was Uranus they found this way. Yeah, I know. Shh, stop.
Is that why you say that?
Oh, yeah.
Oh. Was it that?
Yeah, when I was a kid, it was the other pronunciation. And somewhere along the line, academia changed the pronunciation to Uranus. I think because teachers got tired of all the kids snickering. All right, so the way they found Mystery Planet out here was that this planet was supposed to go through a particular orbit, and they noticed that its orbit was not what they expected, based on the gravity solely from the sun. That it was bowed out, and so they suspected there was some other mass out here from Mystery Planet.
Another sun.
Yeah, it could be, except you don't see it, right? So it's a mystery unknown thing. And so they went looking for it, and they found it. Okay? What's that?
Uranus.
They found Uranus. You tried to trick me. All right. They also do this when they're looking for exoplanets. You know what an exoplanet is?
Outside.
Outside of the solar
A
system.
planet outside of our own solar system. They'll see a star out here that they'll look at, and they'll watch it over time, and it should be stationary in space, because it's so far away. Even though it's moving, we can't see its movement. And what we'll see is that the object will vibrate back and forth slightly. Back and forth, back and forth. And that's due to a planet or another star or something we can't see. It could be a black hole, could be anything with mass, making it wobble back and forth. And that's how they find some of the planets, or that's how they found some black holes as well. All right? Something that they can't see, that doesn't glow. All right, an interesting thing about this is here's you. Big. You are. Put on a few pounds. And here's the Earth. Eating too many bonbons. All right? That's the force of gravity on you. But that's also the force of gravity on you. Right? Your weight is gravity. So weight equals gravity when you're on the Earth's surface, when this radius is the Earth's radius. And you have the mass of the Earth, and this is the mass of YOU. Okay, so let's take a look at this. This is G M1 M2 over R squared equals mg. Now, I've dropped the negative sign because I already know the direction is towards the center of the Earth, right? No big deal. But wait. This radius is the radius of the Earth. This mass is the mass of Earth, and this is the mass of YOU. What mass is that? It's the mass of YOU. So you go away. Because it makes you pay attention. So, wait. So what does G equal?
That.
Equals big G, mass of the Earth, over the radius of the Earth, and that gives you G for the Earth. Okay, you need to know how to do that.
It's radius squared, isn't it?
Oh, thank you. Radius squared. Thank you.
You need to know.
All right? You need to know how to do that. Because they're going to ask you a question like, by the way, if we plug in G, 6.678 negative 11th, if we plug in mass of the Earth, and we plug in the radius of the Earth and square it, Do all the math. What is this going to be? 9.8. Within rounding, it'll be 9.8. Okay? What if we put in mass of Mars and radius of Mars squared?
Well, we have a smaller gravity.
Yeah, but we'll get G for
Mars.
Mars. What if we do it for planet X? Let's say planet X, the mass of planet X equals 1/2 of the mass of Earth. And the radius of planet X is only 1/4 the mass of Earth. Okay? The radius of planet X is only 1/4 the radius of Earth. Okay, first off, tell me 8 times? Bigger or smaller?
Yeah,
It would be 30. Well,
It's 8
it would be
times.
30.
8 times,
Whatever
but then it's
small.
divided
It'd be
by
2 times.
2. So
It'd
it's
be,
like
no, that
4.
would be bigger. 8 times.
Like 4.
Four.
Oh, yeah, 8.
9.
Yeah.
So it's 16 divided by 2. So
8
it's
times 3.
69.
I've been making dumb mistakes.
All right, here's the way you do this. 1/2 the mass of Earth
So stupid.
and 1/4 the radius of Earth, but that's squared, right?
So
So I end up with 1/2 divided by 1/16,
Means a
which leaves 8. 8 what? 8 of GME over RE squared. But what's that?
8.9.
Yeah, that's the G for Earth. So it's 8 times 9.8 meters per second squared. So if you were on that planet, you would weigh 8 times more than what you weigh here. So you'd have a really hard time getting up in the morning and going to school.
so because
Actually,
because the radius is not proportionally changed with the mass. That's what causes.
Yeah, and in fact, what's crazy about this is, look, what if you would proportionally change them? What if this was 1/2 and 1/2?
It would still be greater.
It would still be greater because that's squared, right?
So the radius has to be bigger for it to be less.
So that would be
Yes, or if you had the same mass and the same half the mass and the same radius, that would also give you less, right? Okay, so the radius makes more of a difference than the mass does, okay? So like for instance, Jupiter. If I remember correctly, Jupiter only has an acceleration due to gravity near its surface. Now surface is kind of vague because it's a big cloud, right? It's a big gas bubble planet. And near the surface of the tops of the clouds, the acceleration due to gravity is about 25. It's only about 2.5 more times than Earth, because even though it has so much mass, it's a huge, huge planet, right? So just because the planet is enormous doesn't necessarily mean that it's going to have a huge acceleration due to gravity, because radius is squared. All right. Since, in fact, the density of Jupiter, is that right? Isn't the density of Jupiter and the density of Saturn? I know the density of Saturn is less than the density of water. So if you took Saturn and put it out in the Pacific Ocean, it would float,
Yeah.
sort of.
Because obviously it fits in the Pacific Ocean.
That's right. Of course, the Earth would be absorbed into the planet Saturn, but whatever. That's a small worry, just to see if it floats.
Let's do that.
That's right. We'll do it just for the fun of it.
Then we have the problem of, should we take the Earth to Saturn or bring Saturn to Earth? I think
Saturn to Earth.
I think we just put propellers on the big ring system. We could just fly it through space to Earth. It'd be okay. All right. So we've just done gravity and weight. Gravity and gravity. All right. Spring force. We've already talked about this one, but let's do spring force again. Force from a spring equals negative kx. Okay, you ready?
I use that machine.
Uh-oh.
Me too.
Used it incorrectly?
Yeah. Oh, I don't know.
Okay, if you have a spring has a constant. It's sometimes called the force constant or the spring constant. The spring constant, spring or force, constant, a spring constant or force constant, is equal to the amount of force it takes to stretch the thing a certain distance. Okay? So it's going to have units of newtons per meter. All right? Now, a lot of springs you can't stretch a meter. That's okay. So it's how many newtons divided by how far you actually stretch the thing in meters. All right? So once a spring is built, it'll have a certain spring constant. And we assume that that spring constant to be constant, even though in real life, the farther you stretch something or compress something, the spring constant may change. All right? Like if you take the spring out of a clicky pen, like one of these.
When it puts big as
It's gone.
Oh, man.
Exactly.
Yeah, you're
Here, let me see if I can find one.
Well, you can have the.
All right, so that little spring, if I stretch that a meter, then this sucker won't be a spring anymore, right? Okay, so the spring constant is only in its springiness area, right? All right. So if you stretch it too far, it's going to get messed up. So you've all done that somewhere along the line, I'm sure.
Here, you can use this one to demonstrate.
You need this to demonstrate?
Nobody cares.
Like, just open that.
Open it.
I don't care about the University of Dallas.
All right. So what? You want me to
Yes,
unspringy
like
it?
right here in front of the camera.
Oh my God.
Yes.
What's the?
Yes.
Yeah.
Okay, now, like, what? No, like,
I want you to completely just
like destroy it.
Like that?
Yes.
somewhat springy.
So it's not really a spring anymore. It's a mustache.
It's a modern mustache.
That's right. Modern mustache.
Lauren.
I don't know, it looks like.
Okay. Everybody, the thing about this equation you need to be aware of is right here, x equals 0. And if you go positive and negative,
Touch the same.
the negative sign, why do we have a negative sign?
Because it's 4 to 4.
Yeah, because if you stretch the spring in the positive x direction, the force will be in the negative direction.
Yay.
That's the force from the spring, not the force you apply to stretch the spring. Because you obviously apply the force in the direction the spring's going to go. All right, so we're done with springs. Okay, I'm going to skip tension and normal for a second. Yeah. Actually, here, I'm going to show you ones we don't need to worry about. You ready?
Alright.
For the test.
Oh, yes.
Drag, we don't even worry about drag.
For the
Drag, that's physics C.
Or strong or weak.
Strong or weak, that's college.
Yeah. Wait.
Our college course.
We'll vaguely talk about the strong force, maybe
I know.
in
They have to
nuclear
be
chemistry and in nuclear physics, but very vaguely, okay? All right, the magnetic force,
Physics C.
we're going to skip that for now. The reason we're going to skip the magnetic force for now is because the magnetic force is the strange one that you need the right-hand rules for. Do you remember those things? You'll love them when we get done with them.
That much?
Yes, the ones where you have to look kind of stupid during the test to get the force direction right. Okay, so we're gonna delay this one till later. Okay?
Oh, I never understood the left finger thing.
Me neither.
You'll
I'm
get
not
it.
to my right hand.
You'll get it. I promise. All right? Okay, let's talk about electric force. That one is going to be on our test. All right, electric force. Electric force, you ready?
I'm ready.
All right, what is it? A-E-I-O-U? No. That's our vowels. What is
Charge
it?
1 times charge 2 over the distance between the charges.
All right,
Is it square?
it is
Oh,
squared.
yeah, that.
The same thing
Yeah.
as magnetic.
Yeah, this looks the same almost as gravity.
set the constant.
Yeah, there's a couple of differences between electric force and gravity, okay? So let's make sure we get them straight, otherwise they're applied exactly the same. Okay? So, number one difference is the constant. The constant here is the...
Spring.
This constant is called Coulomb's constant.
Coulomb's law.
Because this is Coulomb's law. Coulomb's constant is 9e9 Newton meters squared per Coulomb squared.
Yeah.
Okay, that's also on your equation sheet, or your constant sheet, I mean. All right? Now, this here you're going to see it written a different way as well. Okay, the different way you're going to see it is it's going to be written like this. 1 over 4 pi epsilon naught.
Yeah.
Did you see that last year?
Yeah.
But some constant sheet.
Okay, it's on the constant sheet.
No.
Okay, k equals this. So that means this equals the same number.
The number's still gonna be on the constant sheet though, right?
That's correct. If you look on your constant sheet, you'll see Coulomb's law constant, k, equals 1 over 4 pi epsilon naught, equals 99. All right? Now, for Physics B students, this seems like the stupidest thing in the world to ever write your equation this way. But you will see it this way. Yeah, that's a pi. And for you this year, this will seem really bizarre. Why would we ever make it so complicated when we would just use k? All right? The reason why is because this is not the most basic constant. There's a more basic constant that uses epsilon. All right? What's epsilon? Good question. It is called the permittivity constant? Permeability constant?
That's not heavy that.
I always get them mixed up.
That's not
It is the vacuum permittivity. Okay, let me write it down. It's 8.85 e to the negative 12 Coulomb squared per Newton meter squared. Now, everybody, you're rarely going to use this, but you will occasionally when we get to E&M, electricity and magnetism.
Next
You're
week?
almost, actually this next semester. Alright, so 1 over 4 pi epsilon naught is the same as k. This is what epsilon is. If you plug epsilon in here, you'll get the same number. Alright, occasionally we'll run into this. It's the vacuum permittivity. Otherwise, you can think of it as the universal electric constant. That's what it is. Alright? Just like this is the universal gravitation constant, this is essentially our universal electric constant. Vacuum permittivity. Okay? Alright. There's another difference between electric force and gravity force. A major, major difference. Anybody know what it is?
Mass and charge?
Yeah. How many types of mass do we have? Exactly. There's only one. You either have mass, a lot of mass, a little mass, or no mass. The mass is mass is mass. How many types of charge is there?
Oh, negative.
There are two.
positive.
Okay, there's positive and negative. All mass is positive. There is no such thing as negative mass. It would be a very scary world if we had negative mass. Watch out for that little area over there of negative mass. It might shoot you into space.
Is that what happened?
Well, yeah, if there was negative mass. But gravity only attracts. Gravity only attracts. That's all it does. This force attracts or repels, depending on the charges, right? So if we have a positive and a positive and a negative, okay, everybody? Tell me, which way will this one go?
Down to the right.
I'm thinking
They go that way.
down,
Downward that way.
down right.
Okay, if this is my green charge, what will the green charge do to the blue one?
Attraction.
It will attract it because When I plug in a positive charge and a negative charge, I'll get a negative force. And what does negative mean again? It means pull in along the radius, or attract. Okay? So I'll get a force this way. Now I want you to be careful. Some of you will write that as a negative force. I'll tell you why you need to be careful about that in just a minute. Okay, my purple charge on my blue charge, what will it do? It will repel. You'll get a positive, because a positive charge and a positive charge will give you a positive force, which means repel, which means push out along the radius. Okay? Now, here's our dilemma. You need to be very careful with this equation, because positive does not mean to the right. It means out along the radius. Negative doesn't mean down. It means in along the radius towards the other one. Okay? The problem we end up with is if we have something like this. What if I put a positive here, and I put a negative here, and I put a positive here, and I want to know what's going to happen. No, let's put another positive, another negative. All right? And I want to know what's going to happen to the blue one again, right here.
It's going to move towards the positive.
Yeah. It's gonna super move towards the positive.
It's going to super move towards the
They're
positive.
practically going to be together.
Inward
getting
along
pushed
the
and pulled.
radius, like double team. Let's go.
All right.
Two directions.
Stop it. The blue one. Which direction is the purple force on it?
Towards the
Towards the positive. But when I plug this in the equation, that's going to be a negative force, right? All right. When I do this one, what am I going to get?
positive by the equation.
A positive force.
Which way's the force?
That way.
Away from the negative.
Yeah.
This way,
As well.
which is a positive force.
And those would count.
Oh yeah, okay, so here, do you see the dilemma you're going to have? What happens is that when you plug the numbers in, you're going to get a negative force for this one. When you plug the numbers in for these two, you're going to get a positive force, because the negative times negative gives you a positive. And if you're not paying attention, what you're going to get is you're going to have a positive force and a negative force, and you're going to end up with adding them together, actually subtracting them from each other, and you don't get the correct answer, right? Okay, here's the deal. Yeah, you might get 0.
They're the same.
Yeah, if they're the same charge in the same radius, that's correct. You'll get 0 when you add them up, when really you should get double the force, right? Okay, everybody, here's my caution. I would like for you here as Physics B students to take the absolute value of this and decide the direction, and then draw the direction on your paper, or decide whether it's positive x or negative x. Because the coordinate system for this is a radial coordinate system. It's not x-y coordinate system. It just means toward or away. That's all it means. So these two, the force is away. These two, the force is toward. Okay? So what I want you to do is make all of your forces positive, and then decide what that direction is, and draw it on your diagram.
Okay, and when we define the direction, we get to define which way is positive and which is negative.
You can, but in general, we'll have normal x-y coordinate system. In most of the cases, it'll be pretty evident which way you decide your coordinate system.
Yeah, like
Yeah, just like our other one. All right. So what if I had a charge here, and a negative charge here, and a positive charge here, and I want to know the direction of the force on this one? Okay, we'll make it on the blue one again. What's the direction of the force on the blue one?
down.
Tell me which quadrant? First, second, third, or fourth quadrant?
And there's quadrants.
Third.
There is quadrant, because there you go.
Third.
Third quadrant?
Yes.
Ish.
So 1, 2, third quadrant down here.
Yeah.
Okay, let's find out. Our purple is our positive one, right? So purple or pink, I'm sorry, positive and positive gives you a force which way?
Away.
Away.
Yeah.
Away. All right, and
Stop.
green, this gives you toward, right?
Well, it depends on the magnitude.
That's
Yeah, it's going to depend on the magnitude, right? But we know it's going to be somewhere between these two, right?
So 30.
So it's going to be somewhere down here. Right? Probably third quadrant. Yes, sir.
When we're like trying to find the forces on a certain charge, do we just assume the other charges are stationary?
All right. Good point. That's one of the fallback, or one of the failings of this equation is that in reality, these assume that all the charges are stationary. So if you have a moving charge, this equation is a little bit challenging for us, right? So we will assume our charges to be stationary. Now, and then just figure out which way the net force is on them, and then what they would do actually is they'd figure out the net force on this one, calculate its acceleration, and for a short period of time they'd see where it goes, then they'd stop them and recalculate the new direction of the force and do it again. Does that make sense? They'd kind of step their way through which way it's going to go. Okay?
Isn't it actually equations?
One second. Yeah. Say that again. If you do it over a shorter and shorter time period for those little steps, yeah, it's very accurate. It's very accurate. But if a whole bunch of them are moving, it turns out to be pretty complicated. But we're just going to see, yeah, they're all, because all of them are moving at once, right? They're all flying around.
like a bunch of little kids.
Okay? Yes, like a bunch of little kids. Yes, Rudy, you had a question.
So that's actually quite one.
There are other equations that work well for them moving around, Gauss's law works pretty good, but we won't talk about any of those until we get into physics C.
We're actually going to do them with movement in physics.
Actually, even in physics C, we'll assume that they're stationary still. Okay? But you know what? We have enough knowledge just with this one to actually set up a computer program that would be able to do it for us. Like I said, all we do is just figure out what the acceleration of it would be, and then just for a short period of time figure out where it's going to go, and then stop, recalculate, do it again, stop, recalculate, do it again.
I don't think I'd be able to make that.
Okay, let's talk about
Friction.
these three
All at once?
all at once. These three, a student of mine one time, I was talking about these. Actually, let me talk to you about them just a little bit and tell you what she said about them, and it's a really good observation. Now, let's talk about these three forces. Let me talk about how they all occur. All three of these forces occur because of atoms. Okay? Because things are made out of atoms.
You gotta put your initials in those boxes.
Yeah, that's right.
Oh yeah, the game's
We're going
awesome.
to do that. I won. All right, so if we have an atomic structure, a very simple atomic structure, we have atoms, and we're talking a solid here. You can't have tension in a liquid. Okay? Because if you take, tension is the pulling apart of atoms. Okay? Compression is the pushing together of atoms. Okay? These are all, well, tension and compression. This is really kind of what we call a shear force.
Normal is compression?
Normal is like compression. Tension is like pulling apart. Okay? Normal is like compression. And friction is like what we call shear. Okay? Shear is when you try to kind of rip them past each other sideways. Okay? So like for instance, if I was to take these and grab hold of these and pull downward, and if these were locked in place, like if this was atoms in a string, and I pull downward, okay,
Stretching.
I'm trying to stretch the atomic structure apart. Well, they're bound together by these bonds, which we can model as springs, right? And so they stretch. Tension is that stretching of the atomic structure, that bonding between them. Okay? That's what tension is. Oh,
James
the hamster. Why?
Because it's James Bond.
Oh, got it. Sorry, a little slow on the uptake there. All right, now, that's tension. Everybody, if I don't pull on it, we don't got no tension.
We don't got
You sound like Lisa.
What, just grab
There's
it?
no gravity pulling on it. The mass of the string.
So
is
Lisa
down.
has
That's
badly
so
English as well?
Yeah, she speaks real country. God, stop, Steve. Well, yeah, but the gravity's pulling it down.
So in Lisaism, if I don't pull on it, I got no tension. Okay? All right. So if I don't stretch the bonds, no tension. Okay? Normal force. Normal force is a compression. If you try to compress them, like if this is the floor and I stand on it. If I stand on it, I compress them. And as I compress them, I compress the bonds and they'll push back.
So are tension and normal just like spring, except on a smaller?
Yes, they are very similar to a spring force or an elastic force, but on an atomic scale. So they're not exactly like a spring force, but they're very similar. Okay, the one that's a little bit different is friction. Friction is when you have something on top of here and you slide it across. When you slide it across, it's going to stretch them side to side. Okay, it's a little bit different. It's called a shear force. When you try and slide them side to side.
So it's moving that way, but it wants to push the other.
That's correct. So what happens is if I have another object on top of this one, we'll make it a different color. Here, I'll make it green, just because.
The color of money.
If I move this one to the right,
Oh, that's why it goes like this. It's like,
yeah, so what happens to these is these get stretched out this way, right?
So we don't want it.
And these get stretched out the other way, right? So what happens is that when I move that one to the right, they will catch on each other, and this will get stretched out this way.
And then the force wants to go the other.
And the other one stretches the other way.
and they're both moving, they're moving in different directions.
That's correct. So this one will get stretched out like this.
No.
No.
Yeah, you were. Okay, no, yeah, I get it.
Is that wrong?
It's because if we're grabbing it from on it.
Oh, okay, you're pushing it
Oh.
this way, right?
And I'm mushing, moving this one this way. Mush. I'm moving it this way, right?
Yeah.
So like these are getting pulled this way, and this bottom layer is getting stretched backwards, right? Take your hands, put them together, okay, and then move one of them up and the other one down, and you can, if you smash them together pretty good, you can see your skin stretch, right? One way and the other, right?
There's not your fingernails.
All right?
I'll give you an example.
So-
Do with red, it's red.
Oh, yeah, yeah.
So that compression, that's what
You couldn't do tension, though.
yeah, you just rips.
Art. All right. So everybody, when you stick your hands together, when you move your hands, you can see your skin stretch one way or the other. When you try to move, okay, when I try to move my right hand up, it gets pulled back down by friction, right?
Well, it's forced back there.
Ah, it's forced back down. The force is hindering its motion, right? But what is the friction doing to my other hand?
It goes something off.
Ooh, you got that?
Say upward.
Yeah.
Yeah, it is.
It's trying to move it up, right? Okay, here you go. It's a common misconception that friction always opposes the way the object is going. That is not true. Okay? So like for instance, I have my calculator. If I take my hand and I move it to the right, ooh, what happens to my calculator? Slides backwards, right? Okay, but if I move it slow, all right? Now, which way is my hand moving this thing?
It's still now.
That way.
My hand has a normal force up on it because the calculator's compressing my hand, right? So I have a normal force up, but then I'm trying to move this way, and what happens is there's friction between me and the calculator. So friction is making the calculator move forward. Ooh, this is really weird. Okay, think about it. You're standing there, and when you walk, what do? You push your foot backwards to move forward, right? You push your foot backwards to move forward. So which way is friction from your foot onto the ground?
That way.
Your friction off from your foot on the ground is pushing the ground which way?
Back.
Backwards. If you don't believe that, stand on a skateboard and try and walk forward. Right? The skateboard goes backwards, right?
You gonna fall.
Okay. But the Earth is such a large mass, the Earth doesn't really go backwards, not much. And so, which way is friction from the Earth on your foot?
Forward.
Forward. So you need friction to push you forward when you walk.
So, like we
Very
have on slidey
strange.
shoes, that's why it's, like,
When you-
when you have on slidey shoes.
Yes, when you have slidey shoes.
Yeah, and it's like, it's not very good.
That's right, not enough friction, right? So you can't move forward.
Yeah.
Or like, say you get on ice skates. When you first learn to ice skate, you're a little kid, and what do you do with your ice skates? You have your ice skates pointing forward, and you're going like this, and you're not going anywhere. So if you want to go forward with ice skates, you have to use the edges of the ice skates to push you forward, right?
Oh, they have fixes for it.
So when you walk, look, I'm walking. All right?
They kind of dig.
You apply friction to the ground this way, and you have friction on your feet this way. They're equal and opposite.
So there's no friction? Wait.
Okay, everybody catch that?
Yeah.
You apply friction to the floor backwards, and you have friction on you forward, making you go forward. But do the frictions cancel?
No. Well,
Okay, look. If I had an object right here, here's you, and if somebody over here pushed your head this way, and somebody over here pushed your head this way, then would the forces cancel?
no, they
Pressure.
They would cancel. Your head would not move either direction.
Yeah, would it be compressed?
Now, I didn't say it wouldn't hurt. I'm just saying, would the forces cancel? And the answer is yes.
Okay, but if the guy was running at an accelerated,
Now, do these two forces cancel?
I guess.
Somebody explain to me why these two forces don't cancel.
Because you're walking that way, so you already have force going that way. Because the sum of the forces is that way.
Oh, you're all missing it. These two forces are applied to one object.
Those are applied to each other.
These two forces are applied to
Separate.
two different objects. Okay, here's the deal. Newton's third law, we've talked about it already a little bit. For every force, there's an equal and opposite direction force. But these two forces never occur on the same object, right? So, when you walk forward, you cause friction on the floor to move the floor backwards, or try to move the floor backwards. And then the friction from the floor tries to move you forward. Since you have less mass than the floor, you go forward and the floor stays put. If you do the same thing standing on a skateboard and you step forward, the skateboard goes backwards because it has less mass, right? Because F equals ma equals ma. Since the floor is attached to the earth, it has a ginormous mass and will have a very tiny acceleration, right? And since you have a small mass compared to the earth, you accelerate forward. But if you do the same thing by standing on a skateboard, it's just the opposite. You move forward only a little and the skateboard moves forward, backwards a lot.
But then
Yeah.
the
It's like
skateboard
those conveyor belts at the airport.
Yes,
The ones that go backwards. And you
That's
go-
correct.
You like zoom.
yes. Okay, look, there's no equation for tension. The reason why there's no equation for tension is because it depends on how much you pull on the object to whether it's going to react or not, right? Like this string right up here hanging from the ceiling, has very little tension in it because only the weight of the string is causing it to be pulled downward, right? But if you pull on it more, it'll have more tension until it breaks. So tension, there's no equation. Normal force is the same way. Okay, how much is the floor right here pushing up? Come on, quick. How much right here?
1 atmosphere.
What happened? Well, could be. I'll buy. Well, no, because there's pressure on the bottom side too. Okay, how much is it pushing up now?
A lot more.
Oh, you.
Yeah, 1 Bruin. That's correct.
That's a standard unit. of measure.
Standard unit of measure.
After that, no.
Unfortunately, that unit of measure is getting larger.
Constant.
It's not a constant.
Yeah, it's an unconstant constant. All right, so now the normal force is my weight. Okay? Because I'm now compressing the atoms. Okay, so no equation. No EQ. No EQ. Friction, on the other hand, we can give an approximate equation. All right? And that is this. Force friction static versus force friction kinetic. Less than or equal to mu or equal to mu force normal. All right, so let's talk about these two. All right? When one object, this is only having to do with friction due to solid objects sliding past each other. Okay, let's get that straight. Solid objects sliding past each other. And we're even talking about solid objects that are non-mushy or rigid. Okay, this doesn't work very good for like tires or Jell-O. Very nice. Okay, it works great for like a box sliding across the floor. It's our simplest friction equation. There's actually a lot of different friction equations. Drag is technically a type of friction, but it's the friction of a solid object moving through a fluid. Okay, so it's a different type of friction. Okay, solid object sliding past another solid object. If it's sliding, kinetic. Kinetic means moving. Then the friction force depends almost entirely on mu and the normal force. Now we know what the normal force is, right? Ooh, I'm glad nobody automatically said it's equal to mg. Because it won't necessarily be equal to mg. All right, we'll show you in just a minute. Okay? Normal force does not necessarily, question mark, equal mg. Yeah, if it's on a slope, it's not. If you're in an elevator, it's not. There's a lot of ways it won't be. All right. This is the normal force. What's that?
He's taking stalker photos of me.
Of the guitar.
All right, mu. Come on, turn around. Turn around, thumb wars. All right, mu equals coefficient of friction.
Are we ever gonna have to memorize like
No.
Give them to us.
As long as you know that coefficient of friction, if it's frictionless, no friction,
it's 1?
it equals 0, right? Because then you get 0 friction. It's 0. And if you have lots and lots of friction, it's around 1. If you get a number greater than 1 for coefficient of friction, you probably need to check your number because you're talking something like Velcro, tape, okay? Yeah, really, really nasty sandpaper on wood or something like that. Okay, I mean, in most cases it's going to be less than 1.
I got my thumbs up.
There we go. Coefficient of friction depends on the two surfaces. Okay? So like for instance, Teflon, on Teflon, really small. Ice, really small. Like metal on ice is really small. If you watch the Olympics, the Winter Olympics, the rails on the bobsleds are like, they're just metal tubes. Okay? And that on ice has a very low coefficient of friction. Alright? You get up to like sandpaper or something like that, it starts to get really high. Okay? Something rough. The rougher it is, the higher this gets.
What
All right.
For skin?
For skin, I don't know. Skin on asphalt, like in an accident, and you fall out of your car.
Fun.
You're screwed.
Too high. We'll just say too high.
You'll leave your skin on the ground.
Yes, you
You'll
will.
keep on going. And
Yeah, so technically the friction is so
You
high
will
that
leave. You will leave a skid mark.
Wear a leather jacket.
Yeah.
it feels my muscles so much worse.
Now, everybody, shh, up here. Up here. Okay. Frowny face. Okay, be very, very careful of this equation. Okay, this is a decoy equation. It tells you what the maximum friction could be, but it doesn't necessarily tell you what it is. Let me give you an example.
What kind of equation is it? A full what?
It's a decoy equation. All right, so here's my question. The question is you have an object right here. It has a mass of 10 kilograms. The coefficient of friction is 0.4, and you're pushing on this thing with 2 newtons. Okay, and it's on a surface where the coefficient of friction is 0.4. What is the and it's stationary.
That's the trick.
Okay, it's stationary. It's not moving. Okay, what's the frictional force? Okay. Well, here's what students. What's your first idea to do? Find
Do
friction
something
force.
like products and
MG.
Friction force equals mu force normal. Actually, if you're really smart, you'll put the less than or equal to in there. You say, okay, well, mu is 0.4. Gotcha. 0.4. By the way, that's a unitless number. Okay, it's just unitless. So you usually try to put mu equals so we know what it is. Okay, normal force. What's my normal force? Okay, well, I got mg down. I got normal force up. And they must be equal, right? Because it's on a horizontal surface. There are no other up and down forces. So that's going to be what? 98?
Yeah.
Okay, so I got 98 newtons. So what's 0.4 times 98?
40.
3.9?
39.2.
39?
0.2.
39.2 newtons. Okay, so you write down that your answer is 39.2. No. This equation only tells you that the force of friction, static friction, is going to be that big or less.
It is 2 newtons.
How do you know it's 2 newtons?
Because the object is staying still, so the force of friction is equivalent to the force being applied to it.
Okay, and this is where
Yeah. that makes
this
sense.
student of mine, she said, so Mr. Bruin, what you're telling me is that friction and tension and normal force, they're all lazy forces.
Yeah.
It's like, that's exactly right. They are lazy forces. They only do what's necessary, right? They only do what's necessary because you're only doing a certain amount of motion to the atomic structure, right? The more you try to compress or stretch or shear the atomic structure, the bigger these forces will be. But if you only apply 2 newtons of force, this thing only needs to be 2 newtons of force. Here's the problem. You need to make sure that you check this out when you're working a problem. If this is 2 newtons and you figure out that the friction force can be 39 newtons, what does that mean?
The object just randomly went backwards.
Yeah, that means that I don't have to worry about getting gasoline in my car anymore. All I got to do is, I want to move that way, I give it a little push this way, and friction takes off this way. Does that happen? No! This is only going to be 2. Wouldn't that be cool? No, that'd be actually really weird. You'd give something a little push, and then it would run you down.
Mr. Bruin, it's a giant wind-up car.
That's right, it's a giant wind-up car.
Yeah, that would be really bad considering how much force it takes to move the Earth. That's how much force it would take to you. Standing up, you'd have that same amount of force applied to you upward.
So we'd not be living here on Earth.
No, we wouldn't.
We'd all be in space.
You know, that would especially be that if like you were pushing it from the front, trying to get it to move forward, and then it just like randomly ran you over?
Right. So since we know that boxes don't randomly run us over when we give them a push, and we know that, by the way, what kind of physics do we violate if this is 39.2?
There's no static friction.
Equal opposite.
Yeah, it violate
Newton's
Newton's
physics.
third law, probably. Well, I don't know. The biggie that it would violate would be conservation of energy, because you'd give it a little push and get a whole lot out of it, right? More out of it than you put into it, right?
For his
It'd be like an explosion.
What's his explanation?
Then it might be static.
Oh, there you go. Guess that's true. All right. So everybody, if we have something that's actually sliding, that's moving, we're very happy because we get to use this equation at will. If we have something that's static, caution, caution, danger, danger, never, ever, ever use this equation unless you know that you are going to be at the maximum value. If you're at the maximum value, then you're going to be at the equal sign, right? And if you're at the equal sign part of it, you're good to go.
It just like starts moving.
Yeah. So if they ask a question like, what's the minimum force to begin moving this box across the floor? Well,
It's a little bit
we have to overcome the maximum friction, so we're good to go. We know we're at the equal sign, not the less than or equal, right?
Wait, hold up. You said that,
Maximum.
like in this case, our maximum is 39.2, so we have to exceed 39.2 to be able to make a move.
All right, good question. Okay, everybody, listen up, because this is always confusing for students. If the question is, here you go. All right, what's the minimum force I need to push this so that it begins to move?
Nice.
And then they give you the coefficient of friction and so forth and so on. All right? The deal is that what we'll do is we'll say if we're pushing horizontal, all we have to do is overcome friction, right? So we'll just say when we get to the maximum friction here, that's our point. You don't have to say this plus a little bit more. You don't have to say that I have to push 39.3 or 39.2 plus a bit. We'll just say 39.2 and we'll call it even. Okay? So that's the break-even point. All right. Now, on your e-homework, there are a couple of problems. We've gone over all the forces that you're going to need to know on the exam. Electric, friction, normal, tension, spring, gravity, weight. I don't know.
Thursday.
So next week, Thursday? Woo, we got to get moving. Now, in your e-homework, there are a couple of elevator problems. Let's talk about those. Okay. The person is standing on a bathroom scale. First thing I want you to realize is the bathroom scale does not measure your weight.
Measures the normal.
It measures the normal force. Because it doesn't magically measure how much gravity is pulling on you. It measures how much force it must apply to push up on you to keep you from falling. Okay? Exactly. Exactly. Now, under normal circumstances, that will be your weight. But not always.
As the acceleration is changing.
Right, so if we draw this person out here, whenever you draw or whenever you solve a problem that has to do with forces, there are 5 steps. You ready? 5 steps. Ready? 5 steps. Step number 1. Draw free body diagram. Always, always, always. Okay, a free body diagram is a diagram of the object you're interested in, and you draw all the forces attached to it. It's best if you draw your forces pointing away from the object just so you can see the arrowheads. It's a little bit easier. Occasionally I'll have students on an exam do this. They'll go, okay, the forces on this person, what are they, by the way? Normal? Which way is normal?
Outward.
Okay, and I'll get students that'll draw that. They'll go, normal. And I'll go, okay, but which way is it pointing?
Antenna.
It's an antenna. An arrow up. What else?
Graviton.
Weight
Gravity.
down. Or gravity. You could call it mg, or you could call it weight, you could call it gravity. Doesn't matter, it's the same thing. Alright? Now, step number 1. Are there any forces acting on the person?
No.
Other than those.
No, that's it.
It's hitting his
There's
head.
wind.
Um,
That's how I say it's windy.
okay, number 2.
This tornado warning yesterday kept on running around
Ouch.
the football.
Oh,
Is it accelerating?
No.
not if it's still.
Oh.
Okay, this is an important question.
Not if the net force is
Accelerating downward.
Alright, let me tell you why this is important, or you tell me why it's important. If you're accelerating up, what does that tell you about these two forces?
Normal's greater.
Normal is bigger than mg.
So you weigh more.
Whoa, whoa, whoa. Which one changes?
Normal.
Why?
Because you're.
Because it's a lazy force, right? It does what's necessary. By accelerating up, do you change how gravity pulls on you?
No.
No. Alright? So this one must get bigger. What if you're accelerating down?
Well, the normal got smaller.
Normal gets smaller.
It got bigger.
What if you're not accelerating?
Well, they're equal.
Then they're equal. So if and only if you're on a flat surface and you're not accelerating, then normal equals mg. Okay? So let's say we're accelerating up. Okay? Step number 3. Step number 3. Coordinate system. Yeah, probably.
No, my hair smells.
Okay, you need to pick your coordinate system. All right, pick coordinate system. Okay, which way do you want to have your coordinate system? First of all, is this a one-dimensional or two-dimensional problem?
2.
I just say
One.
Well,
one-dimensional.
No.
Yeah, because
Yeah,
we're only
Which
having.
We're only doing this, up or down, right? So one-dimensional. So which way do you want to be positive?
Up.
Yeah, I'd pick up. So I'm going to call this positive up. Okay, now, and only now, you build F equals MA. Right, F equals MA for our coordinate system of up being positive. All right, what goes here? How many up and down forces do we have?
2.
Which ones are positive?
Normal.
Which ones are negative?
Graviton.
There you go. You just built F equals MA, and now you solve.
What?
And only now do you solve. Step number 5 is solve. If you follow those steps every time, you will get most of your F equals MA problems right.
Wait, what happened there?
Acceleration?
What happened there?
Yeah.
F equals MA in this direction. I have 2 forces, but one is positive and one's negative. So a positive one and a negative one. And that equals MA. So that means that normal will equal MA plus MG, which equals MA plus G. That means, what will the bathroom scale read when you accelerate up? It'll read fat. Exactly. So if you want to lose weight,
Go on an elevator.
but now wait a minute. Does that mean the elevator can just move down?
Accelerate
It
down.
has to accelerate down. Does an elevator accelerate the whole way
No,
down?
at the beginning.
Yeah, just at the very beginning.
At the end.
So if you bring in a bathroom scale, stand in the elevator, and it accelerates down or moves down, you'll get a lower weight for a little bit, and then it'll go back to normal once you move at a constant rate.
Or you can cut the cord holding the
Or you can
elevator up
cut the
and
cord
all
and
the
you
way
be
down.
weightless.
That's correct. If you cut the cord, then there's no more force up, and you go into free fall. And so normal is 0, and so your acceleration is 9.8, and you have no weight. Actually, that's the easiest way to experience weightlessness.
That's pretty fun, yeah.
Is to go into free fall. So just get in an elevator, cut the cable, and you will
That's smart.
experience exactly what astronauts experience. Exactly. You will not be able to tell the difference
Until you die.
until you hit.
Until the sun
They
falls
don't
at
have
the
this
bottom.
thing called a
What's that myth about if you jump in an elevator?
No.
Survive.
Here you go. Just do
Down
this.
'cause you can jump.
Here you go.
I will die.
Just drill a hole in the earth,
Of course.
Through the earth, not in, through.
through the earth, drop the elevator in.
Okay.
It'll be in free fall all the way to here, this direction.
And then
When it reaches the center,
you stay there.
the gravity will be 0.
So then it'll decelerate.
So you'll overshoot, and now you'll be in free fall that way, but you'll be going this way. And so you go all the way out here,
And you'll end up in China.
and you'll end up in the Indian Ocean somewhere from here.
In other words,
And then you'll go back.
never ending.
Never ending.
That's not very
So
good.
you have to jump out.
second to try to
Right. Yeah, so when you get to the other side of the earth, you have to open the doors and jump out quick and go all the way back.
It's funny because
Now, unfortunately, we have air resistance.
so you'd never be able to get out.
So yeah, what
All that
you do is you
magma.
go to the center of the earth and burn up.
Darn, Ira.
Dang it.